And students, Dave back again with the virtual chem lab. This time we're going to look at a qualitative organic analysis. It's a pretty neat feature of the program. What we can do, we'll start over by clicking down there. Let me grab a ketone, and we're going to do qualitative analysis. You have a choice of cyclohexanone or acetophenone, and what I'll do is I'll grab the acetophenone and transfer some into the round bottom. Bring the round bottom, I'll drag it down to the cork ring. Now we'll do, just for the record, a TLC. Okay, not showing us anything. There it is. You can, of course, save that to the notebook. If we hit save and then OK, I can open up the notebook. And I double-clicked it twice, but then you can examine the TLC, see? So I'll X that out. It's a nice feature. There are unknowns. I won't do one in this video, but you can characterize unknowns chemically or by spectroscopy. Here's the IR of acetophenone. There's your carbonyl stretch, the ketone stretch. Okay, C13, classic C13, your ketone's down right below 200, and the so-called alpha carbon next to the ketone is at 25 ppm. Okay, very nice. Here's the mass spec, fragmentation pattern. You get a nice 105 as the base peak, and that's your base benzyllium ion. You crack a methyl group off from the 15 from the molecular ion, which is 120. They give it to you exact 120.2890. You can dovetail this with the SDBS spectral database online, which carries proton C13, infrared, mass spec, very nice. You can work the two together. Up on the blackboard, they give you the acetophenone boiling point and the percent carbon, percent hydrogen. It's a liquid, so we can't do a melting point. And what we'll do now is double-click on the L-click on the acetophenone, and you'll have a test tube. Look up at the blackboard. You can see zoomed in. And what we'll do, we'll treat the acetophenone with bromine. So I'll transfer with a pipette. You watch the blackboard. Put that in there. And it's starting to stir. It's being heated up too a little bit. You'll see the transition of color as we make alpha bromoacetophenone. And I anticipate that we'll go colorless once the bromination's done. Very nice. And the color's starting to fade. And there you be. So there was a positive test. Double click to get rid of that. Double click on the round bottom to get another sample. And what we'll do now is, for the record, just see if it reacts with potassium permanganate, purple color. Let's put it in there. Let it stir. You're not going to see much happening there. The purple color remains. No oxidation occurs. Ketones don't normally oxidize. Okay. Another sample. Let's treat it with 2,4-dinitrophenylhydrazine. That's a classic. You watch this one. And that's going to change to a precipitate, the 2,4-DNP, the phenylhydrazone derivative. That was the time-honored method of determining structures of aldehydes and ketones by making them into immunoderivatives, such as 2,4-DNP. I'll get rid of that, put another sample up. Let's treat it with hydroxylamine. That would make an oxime. put that in there. And without heating, nothing happens. And even if it were to heat, it would be colorless. So we're not seeing any derivative with the hydroxylamine. I'll put another sample. And now I'm going to treat it with iodine potassium iodide. That should react. And we're getting a iodoform reaction, I would presume. Next one we'll try is get a sample up there. We'll treat it with sodium iodide and acetone and heat. Let's just see what happens. Nothing. So that's your iodoform. The different tests that you could do, the Hinsberg, for all the different functional groups of various tests, along with a spectral characterization. So let's X that out, go to a new experiment, and let's look at, let's take a natural product. And that is acetic acid. So we'll put a sample in there. Notice it's a solid. It's a solid. Let's do the melting point of this. So what we'll do is take a sample over. If I can line it up nicely.
Since these models are driving one of the most significant policy decisions in the history of this country, it's reasonable to investigate.
Okay.
The 2.2 million death was on a chart in the White House briefing room. It came from
Not getting anything from the melting point at this point. I'll have to go back to that. But now, let's put in there sodium hydroxide. I expect that you're going to dissolve that right away. Stir, and there it goes. A little bit of heating too, so we must be decarboxylating. It's going in solution. See it stirring. Clear homogeneous solution. I'll get rid of that. Let me take another sample. Let's try potassium permanganate. Let it stir. Nothing happening, which would expect that would be the case. And I'm surprised I'm not getting the melting point. Let me bring it over. There it is. You have to bring a sample tube over. 153. And if you look up, I think that's citric acid. 153 degrees is the melting point because it's a solid. So it's a very good program. Very, very good program. And you could do unknowns and synthesis. Okay, that's it. Bye for now.